Dear learners, I welcome you once again to this channel. We are still considering rotational motion. In this video, we'll be solving more examples. But at first, we review the several obtained or already considered mathematical formula and expressions. Then also, or briefly, introduce you to, or probably say remind you, principles behind cross-vector product, that is cross product of vectors. And we also have some exercises to try your hands at the end, towards the end of the video. Again, in attempting the exercises, please make your attempt, provide your answer at the comment section. I will respond. Also, if you have clarifications in any part of the video, please provide them at the comment section and I will respond as much as ability can help me. Then let's recall the already considered formulas from our previous videos. L again is the angular momentum, which is the cross product of the radius of rotation and the linear momentum. And because linear momentum is the product of mass and the velocity of the moving body in motion, and because velocity is also a vector quantity, there you bring out the mass and you have mass and the product, or mass times the cross product of the radius of rotation and the velocity, the linear velocity of the moving body. Or you can just use your RP sin theta cross product, because maximum angular momentum is obtained when there is a perfect perpendicular relationship between the linear momentum of the body and the axis of rotation of the body. I think I explained that clearly in the previous video. Then we look at another expression also. Can obtain this also, that is the angular momentum can also be obtained as or in terms of the mass and the velocity. So it's the same thing. Here you have P here, and you have P, you can put your mass and velocity there. So it's the same thing. And recall that linear velocity or tangential velocity is a product of the radius of rotation and the angular velocity of the body in circular motion, radius. So if you substitute that, you have the expression mr squared omega, and the mr squared can be marked as the moment of inertia of the body, the rotation body. Likewise, the torque. And the torque is also the cross product of the radius of rotation and the force acting on the body in motion. The body making a movement about the axis of rotation. So the force acting on that body, the cross product between the radius of rotation and that force, which is RF sin phi. And sin phi is equal to 1. So we have the expression also. can also look at other expression for torque, tau. In this case now, from the Newton's second law, we have our vector F, the force, which we know to be equal to ma. And we know that our A is equal to the radius, product of the radius of rotation and the angular acceleration. So you substitute that, you have it next on the next line, and the final expression is mr squared alpha. Likewise, because mr squared can be taken as moment of inertia, we have tau to be equals to the moment of inertia alpha. So you will need to master all these expressions. You will need to master all these expressions. This expression, you need to master them. You need to master all these expressions. Please do, because you may need to apply any of them. Also, we considered power in the rotating body, which you obtained to be the product of tau, the torque, and the angular velocity. And also, another way of obtaining it from the angle of work done by the body rotating body at the time. You can also have the expression tau equals to omega, the expression. I'm sorry, equals to tau multiplied by omega. Also, kinetic energy of the rotating body can be obtained as half I omega squared, moment of inertia and velocity squared, divided by 2. Those are the expressions we'll be needing them in solving further questions. Let's look at the body. This question: a body whose mass is 5 kilograms moves with a uniform velocity of, and that value of velocity is given in the Cartesian coordinate. So that means the body is considered in two-dimensional plane. When you have things like this, ij, that means you're talking about x, y. So something like this means that it's given in two-dimensional, the x and the y plane. So I is the direction, j is the direction, showing that they are perpendicular. That means that's why it's x and y. So it's given in Cartesian coordinate. And the value of v, velocity, is 2i in this direction plus 2j, j in this direction, beta squared. Now, determine the magnitude and direction of the angular momentum at time t when the particle passes through the point. So, when the particle passes through the point, that is, as the body is moving with respect to the center of axis going around, a point from the center where the body is, as the body rotates, at what time will it pass through the point 1.5 meter, 2.5 meter? This represents r, the distance from the center of rotation, axis of rotation, we call it axis of rotation, r. And this value, 1.5, and you see values are lying in parentheses, this means x, and the 2.5 represents y. So that's just it. Look at that figure on the bottom right side of the screen. The body has a mass m, moves the velocity v. It has a mass m, moves velocity v. Now, what will be the angular momentum? That's L, when it passes through the point 1.5. Okay, so this plane two-dimensional, at what point does it pass through? It's not going in a straight line. So when not going in a straight line, then it's difficult to use one plane. It's going in circular motion, so it's more appropriate. It's two-dimensional. So we see how to go like that. Before then, the concept of cross product of vector will be very essential here. And I briefly introduce you to this concept, or for those who know it before now, just a quick revision. For three vectors A, B, C acting perpendicular one another, as represented by the expression A, B, and C showing their perpendicular direction, I unit directional vector I, directional vector J, and directional vector K. At least, if we have that, A is acting towards I here, B is acting along J direction, and C is acting along the K direction. So you can use this very brief, short approach to know what will happen. Okay? You can use it to know it. So if for cross product of A and B, for example, A I cross B J, the perpendicular means that you use sine. I think you know that before now. So A B sine the angle between the two vectors. That angle, sine of that angle. Because the sine, if and that angle, because they are perpendicular vectors, the angle is 90. So sine 90 is 1. So you have AB. And that value, the magnitude of the cross product of A and B, will act in the K direction. So the action also be perpendicular to both I and J. Likewise, if you have B, C, B is acting along J, C is acting along K. So the product, the magnitude of the two acting forces, will act perpendicular to the individual forces and individual vectors, and that is in the I direction. Likewise, for the third one, I will see from here, this short way to know it. If you are going from I to J, anti-clockwise, IJ. So for IJ, that we have for A cross B, I cross J, then the magnitude of the product will act in the K direction. But if you are going, and that's what you have here, check that is, you have I cross J, you have K. But if you are going anti-clockwise, that is J cross I, look at it here, J cross I, then you have a negative value of K. Negative value of K, direction, the opposite here. If you check the opposite here, if it is J cross I, opposite, all this, also perpendicular to I and J. So for BC now, you have JK. You are going like that, anti-clockwise. Then you have, you see, J cross K. What you have? You have I. And if you go the opposite direction, you go this, KJ. Then you have negative I. That means the resultant vector will go in the negative I direction. So K cross J We not act towards I, we act opposite of I. And likewise for the third one, Ki. Ki, you are going clockwise. So Ki. The resultant vector will act along the J. But if it's clockwise, which is I, K, then as you have here, I cross K, it will act in negative J direction. That is, it will act in the J direction. So, if you understand that, yeah. So that's very important. We need to master this. It's very important for this example and similar examples that we will come across. Okay? Very important for this example and several similar examples that we will come across. But if it were to be two forces acting in the same direction, for example, you have A, two forces, two vectors, A, acting in the same direction. Okay? Then you see, because it is I cross I, and if I cross I means that means the angle between the two vectors is 0. That means they are parallel, they're not perpendicular, and sine 0 is 0. Okay, likewise, J cross J, the resultant vector will be 0. Likewise, K cross K. Okay, so please master it. I cross I is equal to J cross J is equal to K cross K, which is 0. Okay, so master that very well. So let's see the example. Okay, let's see the solution. We have V, which is giving us 2I plus 2J meter per second, and the mass of the body is giving us 5 kilograms. Then the position the body is passing is giving us 1.5, 2.5. That means 1.5 I, 2.5 J meters. And from the formula, now for our L, the angular momentum equals to R cross P, which is, well, because we are given V and M and R, so you substitute MV for P. PA substitute MV for P. And continue to solve. You have your R, which is 1.5 I plus 1.5 J meters. Then cross M, 5 kg. Then V, 2I plus 2J meter per second. So further, you have this, and you solve that scalar times vector, also give you vector. So 5 times 2, you have 10I plus 5 times 2, 10J, then kilogram meter per second. So this expression now is the linear momentum P. We see linear momentum P, but we still need to obtain the angular momentum by the cross product of R. Okay, so do that. 1.5 times 10, you have 15. Then I cross I, you have it. Do you get it? Then 1.5 times 10J, you have 15 I cross J, kilogram meters square per second. Then plus 2.5 times 10, 25 J cross I, you see it, kilogram meter square per second. Then plus 2.5 times 10, that's 25 J cross J, kilogram meter per second. Recall that I cross I means they are parallel. The angle between them is 90 is 0, so sine 0 is 0. So this becomes 0. Likewise, J cross J becomes 0. IJ is K. Sorry, IJ is K. IJ is K. And J cross I will be minus K. So we see the next expression. See, so 0 times 15, that's 0. Then 15K plus 25 minus K plus 0. And the final expression will be 15 kilogram meter square per second K, then minus times plus minus 25 kilogram meter square per second K. And you have answer to be minus 10 kilogram meter square per second K. So angular momentum, we have perpendicular to the axis of rotation and the direction of motion of the linear momentum. Okay? You see K. If you act perpendicular, then. Another example, very similar to what we did now. You also have your 3I, 3J meter per second, and you have so 2, 3. Again, this will be x, y. This will be 2I, then plus 3J. If it is minus here, it will be 2I minus 3J. Okay? Solution again. You have the V is provided, the M 2 kg, and also the R. So you have your L, substitute the values of your R, of your M, and your V. So you solve it, 15I plus 15J kilogram meter per second, then 30I plus I, that's 2 times 15, 30I plus I, 2 times 15 again, 30I plus J, 3 times 15, 45J plus I, then 3 times 15, 45J plus J. And again, I plus I is 0, J plus J is 0. This becomes K, this becomes minus K. Okay, so we have 0 times 30 is 0, then 30K, then plus 45 minus K, then 45 times 0, that's 0. And you have 30K kilogram meter per second, meter square per second, minus 45 kilogram meter square per second. And you have the final expression as minus 15 kilogram meter square per second, acting along the K direction. Okay, so the momentum is minus, angular momentum is minus 15 kilogram meters per second, acting along the K direction. It's perpendicular to the axis of rotation. Or to the plane of rotation, yes. Okay. Another example. Now, the Earth's moment of inertia is given as 8 exponential 37 kilogram meter square. That is 8 times 10 to the power 37 kilogram meter square. Always remember that kilogram meter square is a unit of moment of inertia. So the value given here is R. Now determine its angular velocity. angular momentum and take the radius of the earth to be 60,400 kilometers. So the earth rotating on its axis. The earth rotating on the axis. That rotation, the earth itself has a moment of inertia of 8 times 10 to the power 37 kilogram meter square. Okay? You have to determine the angular velocity with which the earth is rotating and the angular momentum. That's very easy to do, because we know that the earth's rotation takes approximately 24 hours. Or the earth to complete one rotation, one complete rotation takes approximately 24 hours. So let's work with that equation. Okay. Solution. I is 8 times 10 to the power 37 kilogram. Sorry, it should be meter, not it should be meter square, not per meter square. It should be meter square, not per meter square. So this will be an error. It should be kilogram meter square, and the radius is 6,400 kilometers. You have to determine angular velocity omega and angular momentum L. So to obtain the Earth's angular velocity, what do? We know that theta, which is rotation, angular displacement of the body rotating, is omega t. So from there, omega is equal to theta over t. And I said, if for the earth to complete one rotation, to go one rotation, which is 360 degrees or 2 pi radians, then the time to cover that is 24 hours. So that information is what we need. The earth makes one complete rotation. Now, let me use rotation now. Going around the sun, we say revolution, but just going around its axis, on the sun axis, rotating on the sun axis is approximately 24 hours. Okay, so from there, we get the answer in radian per second. Thus, our theta complete rotation, which is 2 pi radians, and time is 24 hours. And in seconds, we have 86,400 seconds. First 24, 1 hour, 60 minutes make 1 hour, and 60 seconds make 1 minute. So to convert from hours to seconds, multiply by 3,600. Okay? So we substitute your value. 2 pi radians over 86,400 seconds. And your answer will be 7.2751 times 10 to the power minus 5 radian per second. So that is the angular velocity. And now that we know the angular velocity and the moment of inertia, straightforward. Recall our formula. Okay? To obtain angular momentum L, where we say that our L equals to I omega, and you substitute your I. Again, don't mind me, this is an error. It should be kilogram meter squared, and the expression times what you have as your omega, angular velocity. And by the time you complete the calculator, you have the answer to be kilogram meter squared per seconds. Kilogram meter squared per seconds. That will be the answer. Okay? The unit will be kilogram meter squared per seconds. The angular momentum. Very straightforward. see if you can have further examples or exercises to work with. Okay, this is an exercise I want you to just work with it. It's a uniform rod of mass 0.20 kilogram and whose length is 1.2 meters. Is hinged freely about the horizontal axis through one end and perpendicular to the rod. The rod is raised so that it is horizontal and then released from rest so that it rotates about the axis in the vertical plane. Now, when the rod makes an angle of 60 degrees with the vertical, you have to calculate its angular velocity and its angular acceleration. Okay? The mass of the rod is given and the length is given. The mass is given and the length is given. Mass is given, length is given. And it said it is hinged freely about the horizontal axis. So you have your rod at one end, it's hinged freely at one end. So let me start from here. This is your rod. Don't mind my rod is not straight. This is your rod. Now, this end is hinged. It's hinged. Okay? It's hinged. Now, you now raise the rod. That's the next thing. You now raise the rod that it is horizontal. So this rod now is now raised. It's now raised so that it is horizontal. You raise your rod, it's horizontal. Okay? The rod is raised. Remember this place is hinged. So if you raise it, it's horizontal. Do you get it? Okay? That means this is the initial position. That means the initial position of the rod. Now, there is now release from rest. At this position now, it's now released from rest. So you have your initial angular velocity, which is 0. So it is released from rest about the axis in the vertical plane. Now, when the rod now makes angle of 60 degrees with the vertical, it now starts falling. At a point, it now makes angle of 60 degrees with the vertical. Maybe at this point now, the rod now gets to this point. And makes an angle of 60 degrees with the vertical. This is the vertical. But when you release the rod, after releasing it, you release it, it falls and makes an angle of 60 degrees with the vertical. Calculate its angular velocity. So that means after it has covered, calculate the angular velocity. Initial velocity at this position is this. Now calculate the final velocity. And if the final velocity is calculated when it has made the angle of 60 degrees with the vertical, that means it has covered this angle, which is 30 degrees, because the angle between the horizontal and vertical is 90 degrees. So that means it has covered an angle of 30 degrees. That means the angular displacement of the rod from rest is 30 degrees. So you have your theta. This 30 degrees is your theta. So calculate the angular velocity. You can do this. Is that not? Sure. The angular acceleration. You can also do it. The mass is known. The length is known. And that length now, which is L, is also the radius of rotation. It's also the radius of rotation. It's known. So, why can't you do it? You can obtain it and also the angle of the angular acceleration too. You can obtain it. I want you to try it. Okay? That question you can also work with. What is the angle at which a point on Earth is displaced after 12 hours? provided the angle of displacement, provide the angle of displacement in degrees and in radians. Okay, you have the heart. Don't mind my drawing. You have the heart. Let's assume the map of Africa. Mind Africa map. Like that. You have North America. You have Europe. It's okay. The equator is here. Don't mind my drawing. It's a little bit that push forward a little bit. Don't mind the. Okay, let me clean that line. Okay, so let me redraw the equator. The equator is just. Okay. Now, you now have a point. Let me use a black spot to show that point. I have a point here. A point here. What will be the angle covered by that point after 12 hours? Do you get it now? So let's assume you take this as the initial, this position now as the initial angular position. Okay? Then what will be the angle, which let's assume it to be 0. What will be the next one after 12 hours? You also need the knowledge, know the Earth's rotation. So you need the knowledge of the time it takes the Earth to complete revolution. And also, do you get it at one rotation? Do you think? Write the answer in degrees. Write in radians. This is a very simple question. Very simple. Also, another example. Consider a wall clock with 3 rotating arms, one each for the hour, the minute, and the second. Now, determine the angular velocity in radians per second of each of the arms. So, calculate the angular velocity of the hour hand, or the minute hand, and the second hand. Can't think about that one. Okay, and the last exercise for you. The Earth revolves around the Sun in an orbit with an average radius of 1.5 exponential 11 meters. That's 1.5 times 10 power 11 meters. That's the result of the orbit. Now, if it has an orbital period of 365.25 days, calculate 1. The angular distance the orbiting Earth moves in 1 day, the angular velocity with which the Earth is orbiting in radians per second, the Earth's tangential velocity